So here's something worth thinking about as you settle in tonight. Right now, somewhere in a building the size of several football fields, a machine is writing poetry. Somewhere else, a different machine is designing a molecule for a new drug that doesn't exist yet. And in a third facility, an algorithm is deciding which stocks to buy and sell, making decisions that will ripple through global markets before you finish reading this sentence. These are the quiet miracles of the artificial intelligence age. They happen billions of times every single day. They write emails, generate images, compose music, translate languages, and answer questions that would have stumped the smartest humans just a decade ago. And for every one of these brilliant digital thoughts to form, a very physical and very tangible amount of energy must be consumed. The machine that writes poetry needs electricity. The algorithm making stock trades needs electricity. The system answering your questions needs electricity. And the vast network that provides all of this electricity, the web of power plants, transmission lines, transformers and substations that we collectively call the electrical grid, is being pushed into a state of stress it was never designed to handle. Not because AI uses too much power, though it does use a staggering amount, but because of how it uses that power. The problem isn't just quantity, it's quality, it's timing, it's rhythm. Think of it this way. Imagine you're driving down a perfectly smooth highway at a steady 60 miles per hour. Your car is humming along, everything is balanced, and the ride is effortless. Now imagine that every few seconds a massive truck pulls onto the highway directly in front of you, then slams on its brakes, then accelerates violently, then disappears entirely. Then another truck does the same thing, then another. The highway wasn't designed for that kind of chaos. The road itself would start to shake. The asphalt would crack. The whole system would become unstable. That is what is happening to the electrical grid right now. The AI data centers are those trucks. They aren't just adding weight to the highway, they are hitting it with a hammer again and again, every single second of every single day. And here is the unsettling truth that most people don't realize. The lights in your home, the charge on your phone, the power keeping your refrigerator cold, all of it depends on a system that is constantly, precariously balanced on a knife's edge. There is no giant battery storing electricity for later use. The grid doesn't have a reserve tank. Every single watt of power you consume must be generated at the exact same moment you consume it. It's a continuous, synchronized dance between supply and demand, and the dance floor is the entire continent. If this balance is broken, even for a fraction of a second, the consequences can be catastrophic. In the worst case, a cascade of failures can ripple across hundreds of miles, plunging entire cities into darkness. This has happened before. In 2003, a single tree branch hitting a power line in Ohio triggered a cascading blackout that left 50 million people without electricity across 8 states and parts of Canada. That was caused by a tree branch. Now imagine what could happen when something far more powerful and far more unpredictable starts pulling on the same strings. At the heart of this delicate balance is something called frequency. In North America, the electrical grid is designed to operate at exactly 60 cycles per second, or 60 hertz. This frequency is the steady, reliable heartbeat of the entire system. Every generator, every turbine, every power plant is synchronized to rotate at a precise speed that maintains that 60 hertz pulse. Think of it as the metronome for the world's most complex machine. When generation matches demand perfectly, the frequency hums along at exactly 60 hertz. When they are out of balance, the frequency begins to drift. If demand suddenly exceeds supply, if a million air conditioners turn on during a heat wave faster than the power plants can ramp up, the frequency drops. It might dip to 59.9 hertz, then 59.8, then 59.7. The generators, sensing this drop, immediately begin working harder, injecting more steam or fuel into their turbines to push the frequency back up. This is a negative feedback loop, and it works brilliantly for gradual changes. The system is designed to handle slow, predictable shifts in load. It is not designed to handle hammer blows. And this is exactly where the problem with AI data centers becomes so dangerous. A modern AI training cluster is not a gentle, predictable load. It is a brutal, pulsating, rhythmic force. A single large language model training session might involve tens of thousands of graphics processing units, or GPUs, all running at maximum power for hours or even days. The power draw of such a facility can be measured in hundreds of megawatts, enough to power a small city. And when the training run ends, or when the system fails over to backup power, or when the workload shifts from computation to communication, that entire city-sized load simply disappears. It drops off the grid in a fraction of a second. This is a phenomenon grid operators are calling customer-initiated load reduction. It is a sudden, unplanned, and massive drop in demand, and it is just as destabilizing as a sudden spike. When a gigawatt of load vanishes, the generators that were supplying that power suddenly find themselves overproducing. The frequency doesn't drop, it spikes upward, violently. The system must then rapidly reduce generation to avoid an overfrequency event that could also lead to a catastrophic failure. It is like a tug of war, where one team suddenly lets go of the rope. The other team goes flying backward, and the entire contest descends into chaos. This isn't a theoretical concern. In the summer of 2025, exactly this scenario played out in Northern Virginia, the region known as Data Center Alley, which hosts the largest concentration of data centers in the world. A minor grid event, a routine fault on a transmission line, caused a momentary voltage dip. The sensitive power protection systems inside approximately 60 data centers detected the dip and simultaneously disconnected from the grid to protect their equipment. In a fraction of a second, over 1,800 megawatts of load vanished from the system. The frequency spiked. Grid operators had to scramble to rapidly scale down generation to avoid a collapse. It was a near miss that sent shockwaves through the industry. Now, you might be wondering, why are data centers so sensitive? Why can't they just ride through a brief disturbance? The answer is the sheer value of what they are doing. An AI training run might be costing millions of dollars per hour. A brief flicker, a fraction of a second voltage sag, could corrupt an entire training run, destroying weeks of work and hundreds of millions of dollars of investment. So data centers are built with enormous power protection systems, including uninterruptible power supplies and massive battery banks. These are designed to instantly isolate the facility from the grid during any disturbance, keeping the servers running on protected internal power. For the data center, this is prudent and necessary. For the grid, it is a disaster waiting to happen. And this is just one aspect of the problem. The GPUs inside these data centers don't just turn on and off as a single block. They have their own internal rhythm, a rapid pulsing beat driven by the demands of the algorithms they are running. A large language model training session is not a steady process. It is a herky-jerky stop-and-start affair. The algorithm processes data in repeated iterations. During the compute phase, the GPUs run flat out, consuming maximum power. Then, for a brief communication phase, where they exchange information and synchronize, the power consumption drops dramatically. These swings can happen dozens of times every second, creating a rhythmic pattern of load variation. This is a phenomenon called periodic AI workload patterning. The load is not just growing and shrinking in a smooth curve, it is oscillating at a specific frequency, often around 1 cycle per second. This rhythmic pulsing of hundreds of megawatts can interact with the natural frequencies of the electrical grid itself. When the pulsing of the load matches or resonates with the natural oscillation modes of the power system, it can trigger a phenomenon called subsynchronous oscillation. These are high-frequency waves of power that can travel through the transmission system, reflecting off generators and transformers. They can cause immense physical stress to massive pieces of equipment. The high-frequency vibrations can literally shake them apart, overheating and causing catastrophic failures. Grid operators are now facing a world where the load is not just large, but also aggressive. The AI data center is a hammer, and the grid is the anvil. The question is not whether the hammer will strike, it is how many times the anvil can take the blow before it shatters. This is why the North American Electric Reliability Corporation, or NERC, the watchdog of the continent's grid, recently issued a rare and urgent Level 3 alert. This is the highest level of warning, reserved for immediate risks to grid reliability. NERC explicitly stated that the rapid growth of computational loads, particularly those used for AI, poses a significant and growing threat to the stability of the electrical grid. The problem is not just about total energy consumption. It is about how that energy is consumed. A traditional industrial load, like a steel mill or an automobile factory, is a steady, predictable consumer. It draws power in a smooth, manageable curve. An AI data center draws power in spikes and dips, in sharp edges and violent pulses. The grid was designed for the former. It is being forced to adapt to the latter. And the adaptation is happening in real time, often with inadequate data and insufficient tools. So, as you lie there tonight, consider this: the device in your hand, the lights in your room, the quiet hum of the appliances around you. All of them are connected to a vast, fragile, and increasingly stressed network. That network is being pushed to its limits, not by the gadgets in your home, but by the unseen algorithms that are reshaping our world. The pulse of the nation is no longer steady. It is beginning to flicker, and the flicker is getting harder and harder to ignore. But what happens when that flicker turns into a full-blown arrhythmia? What happens when the heartbeat of the grid stutters so badly that it cannot recover? The answer is a blackout, but not the kind you might remember from a summer storm. This would be a blackout of a different magnitude, one triggered not by nature, but by technology. And that brings us to the heart of the matter, understanding exactly how a modern AI data center can bring the grid to its knees, and what engineers are racing to do about it. In the next chapter, we are going to take a tour of one of these facilities. We will walk through the rows of humming machines, feel the heat of the processors, and see firsthand the incredible density of power that has become the new normal. Because to understand why the grid is struggling, you first have to understand what is plugged into it. The machines are not just consuming power, they are demanding it with a ferocity that the architects of the 20th century grid never could have imagined. And the collision between the old world and the new is only just beginning. Before we can understand why an AI data center is such a disruptive force on the electrical grid, we need to understand the grid itself. We need to see it not as a collection of wires and poles, but as a living, breathing system, a machine of staggering complexity, the largest and most intricate machine ever built by human hands. It stretches from the massive power plants that generate electricity to the tiny outlets in your walls. It is a web of interconnected components, and understanding its basic architecture is the key to understanding why the new demands of artificial intelligence are so profoundly destabilizing. Let's start at the beginning of this machine. The power plants. These are the sources, the hearts of the system. They come in many forms. There are colossal hydroelectric dams that harness the gravitational pull of falling water, channeling it through massive turbines that spin generators. There are massive coal and natural gas plants where fossil fuels are burned to heat water into steam, which then drives the same kind of spinning turbines. There are nuclear reactors, splitting atoms with controlled precision to generate the heat that boils the water that spins the turbines. And there are the vast, sprawling fields of solar panels, converting the light of the sun directly into electrical current, and the towering wind turbines, their graceful blades capturing the energy of moving air to spin a generator. Each of these sources, whether it is a giant rotating turbine connected to a dam, a gas-fired steam plant, or a bank of solar cells, has the same ultimate purpose. It converts a primary energy source into electrical energy, but the result is the same. They push alternating current, or AC, into the grid. This current doesn't flow in a single steady direction. It oscillates, rhythmically changing direction back and forth. And the speed of that push, the rhythm of that oscillation, is the frequency we just talked about. In North America, that rhythm is 60 cycles per second, 60 hertz. Now, once this power is generated, it has to travel. It has to get from the power plant to the places where it is needed. This is the job of the transmission and distribution system. Think of it as a vast highway network for electricity. The transmission system is the interstate. It uses incredibly high voltages, often hundreds of thousands of volts, to carry electricity over vast distances with minimal loss. These are the massive steel towers you see stretching across the countryside, strung with thick cables. High voltage is essential for long-distance transmission. It is the equivalent of moving your freight in large trucks, rather than 1,000 small vans. The higher the voltage, the more efficiently the power travels. But the power inside those high-voltage lines is far too dangerous and far too powerful to be used directly in your home. It needs to be stepped down. This is where the substations come in. You have seen them, small fenced-in compounds filled with transformers and switchgear. The transformer is one of the most elegant and important inventions in electrical engineering. It can efficiently raise or lower the voltage of an alternating current. At the substation, massive transformers step the voltage down from the hundreds of thousands of volts on the transmission lines to a more manageable level, perhaps tens of thousands of volts. From there, the power flows into the distribution system. These are the smaller lines, often on wooden poles, that run through our neighborhoods. More transformers, often the cylindrical grey cans you see on utility poles, step the voltage down again, finally to the familiar 120 or 240 volts that run your lights and charge your phone. This entire system, from the power plant to the transmission lines, to the substations, to the distribution network, is what is known as the bulk power system. It is a single, sprawling, unified machine. The unifying principle of this entire system, the rule that governs everything, is the principle of balance. At every single moment of every single day, the total amount of power being pushed onto the grid by all the power plants must exactly equal the total amount of power being pulled off by all the consumers. This is the primary, unbreakable law of electrical engineering. There is no significant storage on the grid. It is not like a tank of water that you can fill up and draw from. It is a continuous, real-time flow. Every light you turn on, every phone you plug in, every motor that starts, adds a tiny bit of demand. And somewhere, a power plant must respond by generating a tiny bit more power to match that demand. It is an instantaneous, global dance of supply and demand, conducted across thousands of miles and orchestrated by a combination of automated controls and human operators. Maintaining this balance is the central challenge of grid operation. If generation exceeds demand, the extra energy has nowhere to go. It begins to accelerate the generators, causing the frequency to rise. If demand exceeds generation, the generators are dragged down and the frequency falls. The frequency is the grid's vital sign. It is the meter that tells everyone, instantly, whether the system is in balance. A generator that is perfectly matched to its load spins at a precise speed that produces exactly 60 hertz. If the load increases, the generator slows down slightly and the frequency drops. But a drop of even a fraction of a hertz triggers an immediate response. The generator's governor, a control system, detects the drop and immediately increases the input of fuel, steam, or water, pushing the generator harder to try to restore the speed and bring the frequency back up. This is a classic negative feedback loop, and it works remarkably well for the gradual, predictable changes that characterize the grid for most of its existence. For decades, the electrical grid was a relatively stable system. Load grew, but it grew slowly. Industrial motors, residential heating, office lighting, all of these changed, but they changed in a manageable way. A cold snap might cause millions of electric heaters to turn on, but this happens over hours. It is a predictable, slow-moving curve. Grid operators had decades of experience and sophisticated models to anticipate these changes. They maintained a steady baseload with large, efficient plants that hummed along at a constant output. To handle the predictable afternoon and evening demand surges, they had peaker plants that could be quickly ramped up. The system was designed to handle a few big, slow-moving trucks. It was like a conductor leading a symphony of slow, predictable rhythms. But an AI data center is not a slow-moving truck. It is a hypercar with a 1,000-horsepower engine and no brakes. It doesn't change speed gradually. It can go from 0 to maximum power and back again in the blink of an eye. The power consumption of a hyperscale AI facility is not a smooth, predictable curve. It is a series of steep, rapid spikes and crashes. A single training run for a large language model can cause the entire facility's power consumption to jump by hundreds of megawatts within milliseconds. To the grid, that sudden, aggressive demand is like a colossal, unexpected electrical tsunami. It is the equivalent of a city appearing out of thin air, instantly demanding its share of the highway. And when the training run finishes, or when a system fails over, or when the workload shifts to a less intensive phase, that entire city disappears just as suddenly. This is not just a larger version of a traditional load, it is a completely different type of load, one that exists in a new regime of speed and scale that the grid was never designed to handle. The traditional approaches to load forecasting and grid management are based on statistical patterns and smooth curves. They cannot predict or react to the microsecond scale pulses of an AI training run. The human operators who monitor the grid, sitting in their control rooms watching hundreds of screens, are used to changes that happen over minutes and hours. They are not equipped to handle changes that happen over milliseconds. This is the fundamental disconnect that is at the heart of the current crisis. The hardware of the grid is 19th century physics, the software of the grid is 20th century engineering, and the load is 21st century AI. These three worlds are colliding, and the result is a system that is becoming increasingly fragile and difficult to manage. The engineers who designed the grid couldn't have anticipated the sharp, violent pulses of a modern GPU cluster. They were designing for the predictable rhythm of industry, not the chaotic rhythm of artificial intelligence. And this brings us to another crucial point. The grid's physical infrastructure is not just software. It is made of iron, steel, copper, and concrete. It has physical limits. Transformers can overheat. Transmission lines can sag and melt under excessive load. Generators can be damaged by rapid power swings. The fatigue of the physical components is a real and growing concern. Every sudden power swing is like a small hammer blow to a piece of machinery. Over time, these blows accumulate. The risk of a catastrophic failure, of a transformer blowing out or a generator tripping offline, increases with every sudden, violent load swing. This is a problem that is not just about software and algorithms. It is about the physical integrity of the world's largest machine. So, as you can see, the AI data center is not just a new customer for the grid. It is a fundamentally new kind of load, one that is pushing the entire system into uncharted territory. The slow, predictable world of 20th century industrial load is gone. In its place is a fast, aggressive, and unpredictable new reality. The engineers are scrambling to adapt, but the laws of physics are the same as they have always been. The grid was built for one kind of world. It is being forced to operate in a different one, and the mismatch between the two is the source of the instability we are seeing. The next chapter will look at the specific ways this instability is manifesting and why the warning bells are getting louder every day. So now we understand the machine. We understand the grid as a vast, interconnected system where generation must constantly balance demand. We understand the frequency as its steady 60 Hz heartbeat. And we understand that an AI data center is not a traditional load, but something new, something aggressive, something that pulses and surges in ways the grid was never designed to handle. But what happens when this theoretical problem becomes a reality? What happens when 1 million GPUs, all running in lockstep, suddenly vanish from the grid? The answer is what grid operators now call a customer-initiated load reduction, or CILR. It is the hammer blow, and it is happening more often than anyone expected. The term itself is gentle, clinical. It sounds like something a customer might do voluntarily to help the grid, but the reality is something else entirely. A CILR is an event where a massive computational load, often a gigawatt or more, unexpectedly drops off the grid in a matter of seconds. To put that number in perspective, a single gigawatt is enough to power roughly 750,000 homes. Imagine a city the size of San Francisco or Boston simply disappearing from the electrical grid. The lights don't flicker, they don't dim. The entire load is just gone, as if someone had pulled a plug on a continent-scale machine. The most dramatic example of this occurred in the summer of 2025 in Northern Virginia, the region known as Data Center Alley. This is the place that hosts the largest concentration of data centers on the planet. They sit in long, windowless buildings, stretching for miles across what used to be farmland. The power lines that feed them are among the most heavily loaded in the country. And on that summer day, a routine event triggered something extraordinary. A single 230 kilovolt transmission line, one of the main arteries feeding the region, suffered a fault. This is not uncommon. Faults happen all the time on the grid. A lightning strike, a tree branch, equipment failure. Normally, the grid is designed to handle this. Circuit breakers open, the fault is isolated, and the system reconfigures itself in milliseconds. The lights might flicker briefly, but everything continues. But this time was different. The fault caused a momentary voltage dip. It was brief, a fraction of a second. But for the sensitive power protection systems inside the data centers, it was enough. Uninterruptible power supplies detected the voltage sag and did what they were designed to do. They instantly disconnected their facilities from the grid to protect their equipment from what they perceived as a threat. This was a prudent decision for the data centers. A microsecond of voltage fluctuation could corrupt a training run costing millions of dollars. It could damage hardware worth billions. For them, the protection system was working exactly as intended. But for the grid, the effect was catastrophic. Approximately 60 data centers, all running the same protection logic, all seeing the same voltage dip, all made the same decision simultaneously. In a fraction of a second, over 1,800 megawatts of load simply vanished. The energy that had been flowing into those data centers had nowhere to go. The generators that had been supplying that power were suddenly overproducing. The frequency, the steady 60 Hz heartbeat, shot upward. It spiked to 60.047 Hz, a small number by itself, but a significant deviation in the world of grid operations. The system was thrown into a violent imbalance. Operators in the PJM Control Center, the organization responsible for the grid across 13 Mid-Atlantic and Midwest states, scrambled to react. They had to rapidly shut down generation to avoid an over-frequency event that could have triggered its own cascade of failures. They succeeded. The frequency was restored to normal within 9 minutes, well within the industry standard. But the event sent shockwaves through the entire energy industry. A routine fault, something the grid handles every day, had nearly been catastrophic. Not because the grid failed, but because the load had reacted in a way that had never been anticipated. This was not an isolated incident. A similar event occurred in February of 2025, when another 1,800 megawatts of data center load dropped off the grid. And a year earlier, in July of 2024, a 1,500 megawatt load reduction occurred under almost identical circumstances. These events were not caused by major storms or terrorist attacks. They were caused by data centers doing what they were programmed to do. They were the result of a system doing exactly what it was designed for, and in doing so, threatening to destabilize the larger system it depended on. The 2025 event in particular forced a reckoning. The North American Electric Reliability Corporation, or NERC, the watchdog of the continent's grid, took the unusual and dramatic step of issuing a Level 3 alert, the highest possible severity level. This is not done lightly. A Level 3 alert is reserved for issues that pose an immediate risk to the reliability of the bulk power system. The last time NERC issued one was in response to widespread issues with inverter-based resources like solar and wind tripping offline. This time, the threat was from data centers. The Level 3 alert contained 7 specific, mandatory actions for grid operators and planners. These actions were not recommendations, they were requirements. Transmission planners were told to develop a detailed list of modeling data needed from computational loads. They were told to study their systems with additional consideration for these loads, going far beyond the traditional planning standards. They were told to establish a formal commissioning process for large computational loads, including testing at full load and no load, and to install dynamic fault recording devices to capture their electrical performance during disturbances. The message was clear. The old way of doing business was over. You couldn't treat a gigawatt AI data center like a steel mill or a factory. It was a different beast, with different behaviors, and it required a new approach. The alert also noted that by 2026, data center demand would more than double, and by 2030 it would double again, reaching staggering levels. The problem was not getting smaller, and it's not just about load loss. The same risk exists when loads come back online. A facility that has disconnected to protect itself might suddenly reconnect, causing a massive surge in demand. Or it might transfer to backup generation, creating a different kind of disturbance. Or it might change operating modes, shifting from a computational to a communication phase, altering its power draw in unpredictable ways. Every one of these changes creates a transient that the grid must absorb. The clustering problem compounds this. Northern Virginia, Central Texas, and the Pacific Northwest are becoming massive concentration zones for gigawatt-scale loads. The problem isn't just one data center in one location, it's dozens of them, all stacked in the same transmission zone, all running similar protection logic. If a single disturbance trips one campus, it can cascade across the neighboring facilities, multiplying the frequency impact beyond what any single event represents. The risk of a system-wide cascading failure rises exponentially. And then there is the newest, most disturbing dimension of the problem. It comes from the rhythm of the GPUs themselves. As we discussed in the previous chapter, a large AI training run doesn't draw power smoothly. It pulses. The processors alternate between periods of intense computation, where power consumption is at its maximum, and short communication phases where it drops. This creates a rhythmic, oscillating load that can interact with the grid's own natural frequencies. This is a phenomenon called demand-side subsynchronous oscillation, and it is a nightmare for grid engineers. Subsynchronous oscillations occur when the frequency of the load variation matches the natural resonance frequency of the power system. It is like pushing a child on a swing. If you push at exactly the right moment, the swing goes higher and higher with very little effort. If you push at the wrong time, the swing is chaotic and unstable. The same principle applies to the electrical grid. If the GPU pulse frequency aligns with the grid's natural oscillation modes, it can create a runaway feedback loop. A recent analysis of this phenomenon projected that a 500,000 GPU cluster could create oscillations of nearly 300 megawatts, a force comparable to the event that caused a continent-wide grid oscillation in 2019. This isn't just about total power consumption, it's about the quality of that power. It's about the subtle, rhythmic pulses that can tear transformers apart from the inside and cause generators to trip offline. The industry is starting to respond. Companies like Eaton have released firmware updates for their power quality meters, specifically to detect these high-frequency oscillations. The goal is to give operators an early warning, a chance to see the instability building before it causes a failure. It's the equivalent of putting a health monitor on the grid's bloodstream, but detection is only the first step. The bigger question is how to stop these oscillations from happening in the first place. And this brings us to the heart of the crisis. The grid is losing its ability to absorb these disturbances at the exact moment the disturbances are becoming more frequent and more violent. The traditional sources of inertia, the massive spinning turbines that physically resist changes in frequency, are being retired. The grid is becoming faster, more electronic, and more fragile. The AI data center is the perfect weapon to exploit this vulnerability. The hammer blow is not an accident. It is the inevitable result of two technological revolutions colliding, one that demands ever more power and another that can no longer provide it in the way it used to. In the next chapter, we will look at how the loss of inertia is making the grid more vulnerable, and why the AI data center is the perfect storm that engineers have been dreading for years. So now we understand the hammer blow. We understand how a gigawatt of AI load can vanish from the grid in a fraction of a second, sending the frequency spiking and operators scrambling. But here is the deeper, more unsettling truth. The grid is becoming more vulnerable to these hammer blows at exactly the moment they are becoming more frequent and more violent. The traditional sources of stability, the massive spinning turbines that have physically anchored the grid for over a century, are being retired. And what is replacing them is something fundamentally different, something that, while cleaner and more efficient, lacks the one physical property the grid needs most: inertia. Let's go back to that word, inertia. In physics, inertia is the resistance of any physical object to a change in its velocity. A heavy flywheel, once spinning, resists being slowed down. A massive locomotive, once moving, resists being stopped. In the context of an electrical grid, inertia is the same principle applied to the giant spinning turbines inside power plants. A typical generator rotor in a large power plant can weigh over 100 tons. It is spinning at a precise speed, synchronized with the grid. This massive, rotating mass provides a physical buffer against sudden changes in frequency. Imagine a heavy, spinning top. If you give it a gentle tap, it wobbles slightly but quickly recovers. Its rotational inertia smooths out the disturbance. Now imagine a light, fast-spinning gyroscope. The same tap would send it careening wildly off balance. The heavy top has high inertia. The gyroscope has low inertia. The traditional grid, filled with massive spinning turbines, was like the heavy top. It had high inertia. It could absorb small or even moderate disturbances without breaking stride. The AI data center, with its violent load swings, is like a series of heavy sledgehammer blows to that top. The high inertia of the old grid could absorb many of them, smoothing out the frequency dips and spikes before they became dangerous. but the grid is changing. The push for clean energy has led to the rapid retirement of coal and nuclear plants, the traditional sources of that high inertia. In their place, we are building wind and solar farms. These are essential for a sustainable future, but they are fundamentally different. A solar panel produces direct current, or DC, which must be converted to alternating current, or AC, through an electronic device called an inverter. A modern wind turbine also uses an inverter to connect to the grid. These are what engineers call inverter-based resources, or IBRs. The key difference, and it is a critical one, is that an inverter has no spinning mass. It is a purely electronic device. It can convert power from a solar panel or a battery bank to AC with incredible efficiency. It can even control the voltage and frequency with great precision, up to a point. But it provides no physical inertia. When the frequency of the grid drops, an inverter can't physically resist that drop the way a heavy turbine rotor does. It can't absorb energy from its own momentum. Instead, it must rely on complex control algorithms to try to mimic this behavior, a concept called virtual inertia. But virtual inertia is not real inertia. It is a simulation. And simulations are never as robust as the real thing. The result of this transition is a low inertia grid. A grid that is, in a very real sense, more fragile. A grid where the frequency can change much more rapidly in response to a disturbance. The technical term for this is the rate of change of frequency, or ROCOF. In a high inertia grid, a sudden load loss of a gigawatt might cause the frequency to drift down slowly, giving operators precious minutes to react. In a low inertia grid, the same load loss could cause the frequency to plummet, triggering automatic load shedding or causing generators to trip offline to protect themselves. This is the invisible crisis at the heart of the AI data center boom. The grid is losing its natural defenses at the exact moment the most aggressive new type of load is connecting to it. It is like removing the shock absorbers from a car just as the road gets bumpy. The ride becomes not just uncomfortable, but dangerous. The data bears this out. A study of the Western interconnection, the vast grid covering the western United States, showed a measurable decline in system inertia over a decade of increasing renewable penetration. The ROCOF, the rate at which frequency can change, has been increasing, making the grid more susceptible to the kind of rapid load swings that AI data centers are creating. The rise of large voltage-sensitive loads like AI data centers is compounding this problem, creating a perfect storm of instability. And it is not just about losing old power plants. The sheer scale of the AI demand is making the problem worse. Even as we build new gas plants and nuclear reactors, the total demand is growing so fast that the relative proportion of low-inertia renewable sources continues to increase. This is a classic horse race problem. The grid is being pulled in two directions at once. The urgent need to decarbonize and the immediate need to maintain stability. The AI data center is the wild card that is making this existing tension far more acute. The industry is not blind to this crisis. Engineers are developing new technologies and strategies to address the loss of inertia. One of the most promising is grid-forming inverters. Unlike standard grid-following inverters, which simply track the grid's frequency and voltage, a grid-forming inverter acts like a small power plant. It can set its own voltage and frequency, and it can provide synthetic inertia and fault current, acting like a virtual synchronous machine. It is an attempt to give an electronic device the stability characteristics of a heavy spinning turbine. In Germany, which has aggressively pursued renewable energy, transmission system operators have already mandated that all new grid-connected converters must be capable of grid-forming operation. This is a recognition that the old way of doing things is no longer sufficient. Another critical solution is the deployment of large-scale battery energy storage systems. A grid-scale battery can be programmed to instantaneously inject power into the grid in response to a frequency drop, acting as a synthetic shock absorber. This is called fast frequency response, and it is far faster than any mechanical generator could ever react. The battery effectively provides the virtual inertia the grid is losing. In a low inertia grid, this is not a nice to have, it is a necessity. Some of the most exciting work is happening in the integration of these two ideas. Researchers are developing hybrid systems that combine grid-forming inverters with battery energy storage, creating a single, powerful stability resource. These systems use sophisticated control algorithms to detect a frequency disturbance and respond with precisely the right amount of power injection, stabilizing the grid before the frequency can drop to dangerous levels. The results are promising. Simulations of these hybrid systems show they can reduce the maximum frequency deviation and the ROCOF by over 20%. These are the new shock absorbers, and they are being designed and deployed in real time. The fundamental problem, however, remains one of scale. The inertia of a traditional grid was a collective property. It came from thousands of spinning generators all across the system. Replacing that with virtual inertia requires a massive deployment of electronics and batteries. It is a multi-trillion-dollar engineering project, and the AI data center is accelerating its timeline. The crisis is not theoretical. It is happening now. The grid is becoming more fragile just as the load is becoming more violent. The ghost of inertia is haunting the system, and the engineers are racing to build a new skeleton to hold it together. But the question remains, will they be fast enough? In the next chapter, we will look at one of the most promising weapons in that race, the battery as a shock absorber. We will see how this technology is being deployed to catch the hammer blows and keep the grid's heartbeat steady. So now we understand the hammer blows. We understand how gigawatt-scale AI loads can vanish from the grid in a fraction of a second, sending the frequency spiking and operators scrambling. We understand that the grid is losing its traditional physical inertia at the exact moment the loads are becoming more violent. And we understand that this is not a theoretical problem. It is happening now, in real time, on the world's largest machine. The question is, what do we do about it? How do we catch the hammer blows? How do we keep the heartbeat steady when the source of the disturbance is so fast, so aggressive, and so unpredictable? The answer, or at least the most powerful part of it, lies in a technology that has been quietly revolutionizing the grid over the past decade: the battery energy storage system. But not just any battery, a new breed of battery controlled by sophisticated algorithms designed specifically to absorb the shocks of the AI age. Let's go back to the fundamental physics problem. The grid needs balance. Generation must equal demand. When a massive AI data center disappears from the grid, that balance is broken. The frequency spikes. The only way to restore balance is to rapidly reduce generation or to absorb the excess energy. The traditional solution is to call on fast-ramping gas plants, but these take seconds to respond, and in the world of the hammer blow, seconds are an eternity. The frequency can drift dangerously far in that time, potentially triggering a cascade of automatic disconnections that could lead to a blackout. This is where the battery shines. A grid-scale battery is not like the chemical battery in your phone. It is a massive power electronic system. It can switch from charging to discharging in milliseconds. This is not a mechanical process. There are no spinning turbines to speed up. There is no inertia to overcome. It is a purely electronic response, and it is faster than any mechanical generator that has ever been built. The magic lies in the inverter. The battery produces direct current, or DC. To connect to the AC grid, it needs an inverter, a device that converts DC to AC. The sophistication of the inverter determines the battery's capabilities. The most powerful inverters are called grid-forming inverters, or GFM. Unlike a grid-following inverter, which simply tracks the grid's frequency and voltage, a GFM inverter acts like a small power plant. It can set its own voltage and frequency, and it can respond to disturbances in ways that mimic, and in some ways exceed, the response of a traditional spinning generator. It is like the difference between a passive passenger in a car and a driver who can take control. The GFM inverter enables two critical capabilities: fast frequency response and synthetic inertia. Fast frequency response is exactly what it sounds like. The inverter monitors the grid's frequency at the point of connection. If it detects a sudden dip in frequency, it instantly injects active power from the battery into the grid, helping to arrest the drop. This response happens in milliseconds, far faster than any gas turbine could ever hope to achieve. The battery effectively becomes a massive, virtual shock absorber, instantly pushing back against the hammer blow. Synthetic inertia is even more elegant. Inertia, remember, is the physical property of a spinning mass that resists changes in frequency. A battery has no physical spinning mass, but its inverter can be programmed to emulate that effect. It can respond not just to the frequency itself, but to the rate at which the frequency is changing, a metric called the rate of change of frequency, or ROCOF. When the frequency starts to drop, the ROCOF is negative. The GFM inverter detects this and instantly injects power proportional to that rate of change. The faster the frequency is dropping, the more power the battery injects. This is a near-perfect simulation of physical inertia, and it is one of the most powerful tools in the modern grid engineer's arsenal. The effectiveness of this approach has been validated in simulations. Studies of coordinated BESS systems show that they can improve the frequency nadir, the lowest point the frequency reaches after a disturbance, by significant margins. They can also reduce the ROCOF, giving operators more time to react. In the context of an AI load swing, where the frequency can change in milliseconds, this is not just helpful, it is essential. The industry is already moving aggressively to deploy this technology. A major example is the recent announcement by Cummins that it has been selected to supply battery energy storage systems for a large US data center project. The system is designed specifically to meet utility-defined requirements for managing AI-driven load fluctuations, mitigating load oscillations, and enhancing ride-through performance. It is a direct engineering response to the hammer blow problem. The concept is being refined further. A recent study proposed a line interactive UPS architecture that integrates a grid-forming BESS directly with the data center's power protection system. In this model, the battery sits between the grid and the data center load. Under normal conditions, it passes power through to the load, but during a disturbance, it provides instantaneous voltage and frequency support, effectively isolating the data center from grid transients and smoothing the load profile from the grid's perspective. A series reactor is placed at the point of connection to channel fast transients into the BESS, reducing the grid's exposure to the data center's rapid load swings. This is not just a battery, it is a structural part of the data center's power architecture. The potential of this technology is being recognized at the highest levels. Utility regulators are starting to embrace the concept of flexibility as a solution to the interconnection crunch. A recent report, co-authored by researchers from Princeton University, argued that data centers could shorten their wait for grid connection by 3 to 5 years by combining bring-your-own-capacity arrangements with flexible grid connections. Batteries are central to this concept. By agreeing to operate flexibly, to charge or discharge in response to grid conditions, data centers can connect to the grid faster and at a lower cost than the traditional build first, connect later model. This is a fundamental shift in how the grid is being designed. But the battery is not a silver bullet. It is a component of a larger solution. One of the challenges is the limited discharge duration of a battery. It can provide a massive burst of power for a few minutes, but it cannot sustain that output for hours. If a data center load remains unbalanced, a battery alone cannot fix the problem. This is why a multi-layer approach is needed. Fast frequency response from batteries to catch the hammer blow, primary frequency response from generators to stabilize the frequency, and secondary frequency response from automatic generation control to restore it to nominal. There is also the problem of coordination. A battery that responds too aggressively can create a secondary frequency dip after it has discharged its energy. A battery that is not controlled properly can interact badly with other grid components. This is why advanced control algorithms, including fuzzy logic control and coordinated hierarchical control architectures, are being developed to optimize the performance of BESS in low-inertia grids. The battery is not a simple device. It is a complex, dynamic component that must be carefully integrated into the larger system. The battery is also creating a new market. With the accelerating deployment of BESS for AI data centers, major industrial players are scaling up production. Companies like Cummins are positioning their BESS solutions as critical enablers for data center growth, designed to maximize available grid capacity, manage peak demand, and meet utility-defined load management requirements. The battery is not just a technical solution. It is becoming a strategic asset. So, as you can see, the battery is emerging as the shock absorber for the grid of the AI age. It is the technology that can catch the hammer blows, provide the synthetic inertia that the grid is losing, and help keep the frequency steady. It is not a replacement for the grid, but it is an essential component of a new, more flexible, and more resilient electrical system. The question now is not whether we will deploy these systems, but how quickly and how intelligently. In the next chapter, we will look at the software and the microgrid, the other layers of the new defense system. We will see how the grid itself is becoming smarter, and how the data center is evolving from a passive load to an active participant in the stability of the grid. We have established that the grid is becoming more fragile at the exact moment the load is becoming more violent. We have seen how batteries, with their millisecond response times and grid-forming inverters, can act as the shock absorbers that catch the hammer blows. But here is another layer of the solution, one that is even more elegant and potentially more powerful. It is the idea that the grid itself can become smarter, that the data center, instead of being a passive, chaotic load, can become an active, intelligent participant in grid stability. This is not a fantasy. It is the direction the industry is moving, driven by the twin pressures of necessity and technology. The first layer of this software safety net is the realization that the grid cannot manage AI loads with the same tools it used for steel mills and factories. The physical hardware of the grid was designed for slow, predictable changes. The software that runs the grid was built for that same world. The AI data center is forcing a fundamental rethinking of both. NERC's Level 3 alert was the most dramatic signal of this. It wasn't just a warning. It was a mandatory set of essential actions that fundamentally changed how grid operators must treat these new computational loads. The Level 3 alert contains 7 specific, mandatory actions that every grid entity in North America must now follow. They were not recommendations. They were requirements. Transmission planners were told to develop a detailed list of modeling data, settings, and parameters needed from computational loads. This was a recognition that the old approach of treating a data center like a large industrial motor was dangerously insufficient. You can't just know its maximum power draw. You need to know its ramp rates, its power factor, its protection settings, its trip behavior during voltage and frequency events, and the exact composition of its load. Separating the IT equipment from the cooling and supporting infrastructure. Planners were told to study the stability margins in their area at least annually for zones that contain computational loads. And crucially, they were told to establish a formal commissioning process. This means that before a new hyperscale AI data center can connect to the grid, it must be tested at full load and no load. Its protection settings must be coordinated with the grid's own protection schemes. Dynamic fault recording devices, a kind of electrical black box, must be installed to capture the facility's electrical performance during disturbances. The message was clear. The old way of doing business was over. A 1 gigawatt AI load was not just a customer. It was a system-impacting entity, and it needed to be registered, modeled, and operated with the same rigor as a power plant. NERC is now in the process of formalizing this by creating a new computational load entity category. If finalized, facilities with aggregate loads of at least 20 megawatts, connected at 60 kilovolts, and containing more than 1 megawatt of IT load, will be brought under the same NERC compliance framework that governs generators and transmission owners. But regulation is only one part of the software safety net. The other part is the development of new technologies and operational strategies that actively manage the load. One of the most promising is the concept of workload modulation. The idea is simple and elegant. Instead of letting all the GPUs in a data center start a training run at the same time, creating a massive, synchronized power spike, the software can stagger them. It can phase the compute cycles so that the aggregate load profile is smoother. This is exactly what the research is showing. A first principles analysis of the oscillations created by hyperscale AI clusters found that a 500,000 GPU facility could create oscillations of nearly 300 megawatts. That is comparable to the 200 megawatt forcing event that caused a continent-wide grid oscillation in 2019. But the same paper showed that mitigation through software and partial synchronization can significantly reduce these worst-case projections. This is where the industry is heading. The Electric Power Research Institute's DC Flex initiative is testing exactly these concepts at 9 demonstration sites across the United States, with a founding coalition that includes Google, Meta, NVIDIA, Oracle, National Grid, and the Electric Reliability Council of Texas. The goal is to demonstrate how data centers can actively support grid reliability by adjusting their load in response to grid signals. Instead of being a source of instability, the data center becomes a flexible, dispatchable resource. It is the opposite of the CILR failure mode. And then there is the microgrid. We touched on this earlier, but the software dimension makes it even more powerful. A microgrid is a localized system that can operate autonomously, independent of the main grid. It might have its own generation source, like a large natural gas turbine plant, a solar farm, or a battery bank, or all three. The idea is to build the data center and its power source as a single, integrated entity. This is becoming increasingly popular as a way to bypass the long, multi-year queues for grid interconnection. Companies like Cummins are seeing enormous demand for their natural gas generator sets as a prime power solution for data center microgrids. Instead of waiting 3 to 7 years for a transmission line upgrade, a data center can deploy its own on-site power in as little as 4 to 12 months. The software that runs this microgrid acts as a mission-critical operating system for the site's power infrastructure. It dynamically balances power flows, maintains voltage and frequency stability, minimizes generator cycling, and ensures the rapid response required by the highly dynamic AI compute environment. The integration of a battery energy storage system, or BESS, is critical to this model. A BESS with grid-forming inverters can act as a line interactive UPS for the entire data center campus. During a grid disturbance, it can instantly disconnect from the grid and support the load, preventing the data center from tripping offline and creating that massive load loss event. The smart software coordinates all of this, treating the generation, storage, and load as a single, unified power plant. But even with all this software, there is one more layer of protection needed. It is the ability to see the instability before it becomes a catastrophe. This is where the newest engineering solutions come into play. The industry is now deploying advanced monitoring systems that can detect the subtle signatures of subsynchronous oscillations, the hum that can shake the machine apart. These systems use high-fidelity waveform data and edge-based processing to identify the early warning signs of instability and alert operators before damage can occur. The grid is no longer a static, predictable system. It is becoming a dynamic, intelligent network where the loads themselves are part of the control system. The software safety net is being woven from regulation, workload modulation, microgrid control, and advanced monitoring. It is a new kind of architecture, one that is designed for the speed and volatility of the AI age. And it is only just beginning to take shape. In the next chapter, we will look at the invisible threat of subsynchronous oscillations, the way AI workloads can create a hum that can tear transformers apart, and the new technology being deployed to detect and stop it. So, we have followed the journey of the hammer blow. We have seen how a gigawatt of AI load can vanish from the grid in a fraction of a second. We have seen how the grid is losing its physical inertia at the exact moment the loads are becoming more violent. We have seen how batteries, with their millisecond response times, can act as shock absorbers, catching the worst of these blows. And we have seen how software and microgrids are creating a new, smarter safety net. But there is a deeper layer to this story. A layer that operates at a frequency you cannot see or hear, but one that can tear the grid apart from the inside. It is a phenomenon called subsynchronous oscillation, or SSO. It is not a hammer blow, it is a hum, a persistent rhythmic pulsation that can build until it shatters the very equipment it is passing through. To understand it, we need to go back to the rhythm of the GPUs. As we discussed in Chapter 3, a large AI training run does not draw power smoothly. It pulses. The processors alternate between intense periods of computation, where power consumption is at its maximum, and short communication phases where it drops. This rhythmic cycling, often happening at a frequency of around 1 cycle per second, creates a persistent power fluctuation. In the world of electrical engineering, this is called a forcing function. It is like a person rhythmically pushing a child on a swing. Each push is small, but if it is timed correctly, it can build the swing to dangerous heights. The same principle applies to the electrical grid. The grid has its own natural resonant frequencies. These are the frequencies at which the system wants to oscillate, like a guitar string tuned to a specific note. These natural frequencies are often very low, in the subsynchronous range, below the 60 Hz fundamental frequency. When the rhythmic pulsing of the AI load matches one of these natural frequencies, the oscillations can begin to build. This is a demand-side, subsynchronous oscillation. It is not a single sudden event. It is a gradual amplification, a resonance that can grow over minutes or even hours. The power pulses from the GPUs are small, but they are persistent. They act like a tiny rhythmic hammer, tapping on a massive piece of machinery. Each tap alone is harmless, but 1 million taps, all timed precisely, can shake that machinery apart. And the grid is full of massive pieces of machinery, 100-ton generators, giant transformers, and thousands of miles of transmission lines. The physics behind this is now well understood. A first principles analysis of a large AI cluster projects that a 50,000 GPU facility could create oscillations of approximately 29 megawatts. That is a significant amount of power, enough to cause serious stress on local grid components. But as the clusters scale, the problem becomes staggering. A planned 500,000 GPU equivalent facility could create oscillations approaching 288 megawatts. To put that number in perspective, the 2019 event that caused a continent-wide grid oscillation in the Eastern Interconnection was driven by a forcing function of only 200 megawatts. The AI load of the near future is capable of creating a disturbance more powerful than the one that shook an entire continent. This is not just a theoretical concern. The industry is already grappling with the consequences. In September of 2025, Eaton, a major power management company, released an industry-first solution specifically designed to detect AI-induced subsynchronous oscillations. The solution, delivered as a firmware update to their existing Power Expert quality event analysis systems, is a recognition that this threat is real and immediate. What makes the threat so dangerous is the potential for damage. SSOs are not just about frequency instability, they are about physical destruction. The oscillations create high-frequency vibrations that can literally shake transformers apart from the inside. The mechanical stress on the windings can cause overheating, insulation breakdown, and catastrophic failure. The failure of a single large transformer can be a multi-million-dollar event and can take months to replace. The failure of multiple transformers, all stressed by the same rhythmic hum from a nearby AI data center, could be a grid-scale disaster. The challenge for engineers is that detecting SSOs is not trivial. The oscillations are low frequency and can be masked by normal grid noise. The traditional approach is to monitor the grid with high-fidelity waveform data, streaming it to a central computer for analysis. But this stream-and-catch architecture faces significant bottlenecks. The sheer volume of data is enormous. Communications networks struggle to handle the throughput, requiring data to be decimated or reduced in resolution before it can be transmitted. This decimation means that the subtle signatures of an SSO can be lost before they are ever analyzed. The newer, more elegant approach is edge-based processing. Instead of streaming the data to a central computer, the processing is done right at the source, on the metering device itself. This eliminates the communications bottleneck, drastically reducing latency. The meter can detect an event in real time as the data is being captured and send an immediate alert. Eaton's new solution is a direct implementation of this edge-based philosophy. The PXQ meter, already deployed in thousands of data centers, can now analyze its own high-resolution data to identify the spectral signature of an SSO and alert operators before it can cause damage. This is a critical development. The grid is becoming a more complex, dynamic environment, and the loads themselves are generating disturbances that can shake the system apart. The hum from the AI data center is a new kind of threat, one that requires a new kind of detection and a new kind of mitigation. The edge-based analytics from companies like Eaton are the first line of defense, the sentinels that can warn of the instability before it becomes a catastrophe. But detection is only the first step. The next step is mitigation. How do you stop a subsynchronous oscillation once it has started? The answer, once again, lies in advanced control systems. A grid-forming inverter, integrated with a battery energy storage system, can actively dampen these oscillations. By injecting power that is precisely out of phase with the oscillation, the inverter can cancel it out, like noise-cancelling headphones cancelling out ambient sound. This is a sophisticated form of active damping, and it is one of the most promising applications of grid-forming technology. The research is clear. Hybrid systems that combine grid-forming inverters with battery storage can effectively dampen the subsynchronous oscillations caused by AI workloads. The inverter acts as a virtual damper, absorbing the energy of the oscillation and preventing it from building to dangerous levels. This is the engineering equivalent of a shock absorber for the hum. The grid is changing. It is no longer just a system of slow, predictable machines. It is becoming a complex, dynamic environment where the loads themselves are generating disturbances that can shake the system apart. The hum from the AI data center is a new kind of threat, one that requires a new kind of detection and a new kind of mitigation. The edge-based analytics from companies like Eaton are the first line of defense, the sentinels that can warn of the instability before it becomes a catastrophe. In the next chapter, we will look at the next layer of protection, the physical isolation of the microgrid, and the redesign of the data center's own power architecture to contain the beast within its own walls. We have seen the hammer blow, we have felt the ghost of inertia, we have watched the battery catch the shock, we have listened to the hum that shakes the machine. And now, we must confront the most fundamental question of all. How do you build a power system that can contain the beast? The AI data center is not just a load, it is a force of nature, a creature of immense power and violent temperament. You cannot simply plug it into the old grid and hope for the best. You have to build a cage around it. You have to redesign the entire power chain, from the moment the electricity leaves the high-voltage transmission line to the moment it enters the microscopic transistors of a GPU. This is the architecture of containment. It is a new philosophy of power delivery, one that recognizes that the AI data center is not just another customer, but a sovereign entity. It needs its own power ecosystem, designed from the ground up to handle the intensity and volatility of its unique demands. This philosophy has a name. It is called the grid-to-chip approach, and it is reshaping the entire data center industry. The problem begins with the sheer density of power. A traditional data center rack, the kind that has been running the internet for 2 decades, might draw 5 to 10 kilowatts. A single rack in a modern AI data center, like NVIDIA's GB200 NVL72 system, can demand over 120 kilowatts just to run. But the industry is moving fast. The next generation of racks, designed for the even more powerful Vera Rubin and Kyber architectures, will push past 600 kilowatts. And some industry leaders, like the CEO of Vertiv, are already talking about the 1 megawatt rack as a near-term reality. To put that number in perspective, 600 kilowatts is enough to power roughly 500 average American homes. A 1 megawatt rack is enough to power over 800 homes. And an AI data center will have hundreds or even thousands of these racks. This is not just a matter of scale, it is a matter of physics. At these densities, the old ways of delivering power simply break down. A traditional data center uses 480 volts AC, stepped down to 48 volts DC at the rack level. At 600 kilowatts and 48 volts, the current would be over 12,500 amperes. The copper cables required to carry that current would be thicker than your arm, and the heat they would generate would be catastrophic. The losses would be enormous. The system would be unsafe and impractical. This is the moment when the old architecture must be thrown out. The solution, now being championed by companies like Delta and Eaton, is to move to a much higher DC voltage, 800 volts. Think of it like a water pipe. To deliver the same amount of water, you can either use a wide pipe at low pressure or a narrow pipe at high pressure. The wide, low-pressure pipe is like the old 48-volt system. It works, but at 600 kilowatts, the pipe would be so wide it wouldn't fit in the building. The high-pressure narrow pipe is the 800-volt system. It uses a much higher voltage, which means the current is far lower. At 800 volts, a 600-kilowatt rack only needs about 750 amperes, a manageable current that can be carried by cables that are a fraction of the size. The benefits of this high-voltage DC, or HVDC architecture, are immense. By reducing the current, you reduce the resistive losses in the copper, making the entire system more efficient. Delta reports that this architecture can improve end-to-end power efficiency from about 87.6% to over 98.5% at certain stages of the power chain. In a 1,000 megawatt data center, this efficiency gain can translate into annual electricity savings of over $17 million. You also dramatically reduce the amount of copper needed, which lowers material costs and makes the system lighter and easier to install. Eaton and Train have collaborated on a new reference platform that uses this MV architecture to reduce copper use by up to 80% and installation costs by 30%. This is not just an incremental improvement, it is a foundational reset. The grid-to-chip philosophy extends beyond just the voltage level. It is about redesigning every component of the power chain to work in harmony. Delta's 800-volt DC ecosystem is a complete solution, from the incoming medium-voltage AC to the final voltage needed by the chip. It includes a solid-state transformer that converts medium-voltage AC directly to 800-volt DC bus. It includes an HVDC power distribution board that enables 800-volt to 12-volt outputs at peak efficiency. It includes an energy variance appliance, or EVA, rack designed to maintain a limited peak-to-average AC input current ratio, using energy storage to smooth the GPU peak load profiles. It is a fully integrated system designed to handle the specific, violent nature of AI workloads. This is the architecture of containment. It is a recognition that the AI data center cannot be treated as just another customer. It requires a dedicated, purpose-built power infrastructure designed from the ground up to handle its intensity and volatility. The grid-to-chip philosophy is the engineering answer to the hammer blows, the hums, and the inertia loss. It is the cage that contains the beast. But containment is not just about the internal power architecture. It is also about the physical location of the data center. The industry is increasingly moving away from the traditional model of building data centers near population centers. Instead, they are being built near sources of abundant, reliable power. This is the behind-the-meter model, where the data center builds its own power plant on site. It is the ultimate expression of sovereignty, and it is the subject of our next chapter. We will see how some data centers are bypassing the grid entirely, creating their own private power kingdoms. But as we will see, building a private power plant comes with its own set of engineering challenges. So we have explored the architecture of containment. We have seen how the grid-to-chip philosophy, with its higher voltages and integrated power chains, is designed to handle the immense density of AI compute within the walls of the data center. But here is the next logical step in this journey. If the AI load is too violent for the grid, and if the grid is too slow and fragile to handle it, why connect to the grid at all? Why not build your own power plant? Why not create a sovereign, self-contained energy kingdom? This is the promise of the behind-the-meter, or bring your own power model. It is the ultimate expression of the microgrid philosophy, and it is one of the most significant trends in the data center industry today. The idea is deceptively simple. Instead of waiting years for a utility to upgrade transmission lines, build a power plant on the same site as your data center or immediately adjacent to it. Power the facility directly from that plant, bypassing the public grid entirely. The motivation is powerful: speed. The traditional path to grid connection is a torturous, multi-year process. The average time to connect a new, large load to the grid is now over 4 years, with some projections stretching out to 2031. For an AI company racing to bring a new training cluster online, 4 years is an eternity. A behind-the-meter solution can be deployed in as little as 12 to 18 months. It is the difference between leading the market and being left behind. Across the United States, this model is rapidly gaining traction. In the first half of 2026, developers announced more than $214 billion in projects involving behind-the-meter generation for data centers. Over $2 billion of that is already under active construction. The most prominent example is Meta's Prometheus data center complex in New Albany, Ohio. There, Meta is constructing 2 separate natural gas-fired power plants, each rated at 286.5 megawatts, to power its campus. The first is expected to come online this year, the second in early 2027. The data center is not waiting for the grid, it is building the grid itself. Texas, with its deregulated energy market and business-friendly climate, has become a particular hotbed for this activity. In Fort Stockton, Pacifico Energy is building a massive 1,300 megawatt gas-fired facility to power its data center campus, with 21 Siemens turbines and a 500 megawatt battery energy storage system. The company has even grander plans, with up to 5.3 additional gigawatts of generation in the works. Poolside AI's Project Horizon is adding another 576 megawatts of on-site gas generation in the same region. Meanwhile, Cummins has announced a major agreement with Cersei Energy to supply a fleet of high-powered natural gas generator sets for a behind-the-meter microgrid in West Texas. The model is scaling rapidly, and natural gas is the fuel of choice. The business case is not just about speed, it is about control. By owning the power plant, the data center operator controls the entire energy chain, from fuel procurement to power delivery. They are insulated from utility rate increases. They can schedule generation to match their own load patterns. They can ensure the quality of the power delivered to their sensitive equipment. For a facility that lives or dies on uptime, this is an enormous strategic advantage. Utilities have a complex relationship with this trend. On one hand, they fear losing their largest and fastest growing customers. On the other hand, they are adapting to it. In Wyoming, where data center demand is exploding, Black Hills Energy has a formal, large load tariff designed explicitly to handle these new loads. The principle is simple. The cost causer is the cost payer. A massive new data center that wants to connect to the grid, even if it brings its own power, must pay for any new infrastructure required to serve it, from transmission upgrades to new substations. This keeps the financial burden from being shifted to ratepayers. Under this system, a large customer like Project Jade, a 2.7 gigawatt facility that could ultimately scale to 10 gigawatts, is required to build or contract for its own dispatchable, on-site power. The tariff ensures that the data center bears the full cost of its integration, protecting existing customers from rate hikes. This is the regulated, responsible version of the behind-the-meter model. But there is a catch. The model of total sovereignty, building a private power plant and never touching the public grid, is appealing in theory, but problematic in practice. First, building a large power plant, particularly one that runs on natural gas, comes with its own set of environmental and permitting challenges. A recent report identified at least 74 new fossil fuel-fired power plants planned to directly power data centers, which would release nearly 662 million tons of greenhouse gases per year, equivalent to the emissions of the entire country of Australia. Second, and more critically from our engineering perspective, the behind-the-meter model does not eliminate the technical challenge of AI power swings. It merely relocates it. Instead of a problem for the grid, it becomes a problem for the private microgrid. The gas turbines and reciprocating engines that are the workhorses of these on-site plants are not designed to handle the hammer blows of load steps that an AI workload creates. The rapid, tens of megawatt swings in power can cause immense physical stress to the rotating machinery, leading to high maintenance costs, early retirements, and even catastrophic failures. A microgrid is not a simpler system, it is a smaller, more fragile one. Without the immense inertia of a large public grid to buffer the load swings, the private microgrid's turbines must respond directly to the AI's rhythm. This is a recipe for instability. The very volatility that makes AI data centers a threat to the public grid becomes an even more acute threat to their own private power supply. The solution, once again, is the battery. A battery energy storage system, acting as a buffer between the violent AI load and the slower responding turbines, is essential for this model to work. The batteries absorb the microsecond-scale power spikes and fill in the troughs, smoothing the load profile. This load smoothing protects the expensive turbines from the worst of the abuse and allows the microgrid to operate in a more stable, efficient manner. It is a second-order engineering solution. You are building a new power plant, but you are still relying on the same battery technology to make it work with the AI load. This is the central tension of the behind-the-meter model. It promises sovereignty, speed, and control, but it does not promise simplicity. It replaces one set of challenges, the limitations of the public grid, with another, the technical complexity, capital cost, and operational fragility of a private power system. The architecture of sovereignty is an act of immense engineering ambition, and it is only just beginning. In the next chapter, we will look at a different vision for the future: the AI data center as a grid asset. Instead of isolating the load, this model embraces it, turning the data center into a flexible, dispatchable resource that actively helps stabilize the grid. It is the most radical shift of all, and it could be the key to a sustainable, stable energy future. So, we have traced the entire arc of this crisis. We have felt the hammer blows of gigawatt load losses. We have watched the ghost of inertia haunt a grid that is becoming faster and more fragile. We have seen the battery deployed as a shock absorber and the microgrid built as a fortress of sovereignty. We have listened to the hum that can shake the machine apart, and we have explored the architecture of containment designed to keep the beast within its cage. But here is the most radical idea yet. What if the data center is not just a problem to be contained? What if it is part of the solution? What if the very thing that is destabilizing the grid can be transformed into a tool for stabilizing it? This is not wishful thinking. It is the direction the industry is moving, driven by a simple, powerful insight. A data center is not just a load. It is a massive, flexible, controllable piece of hardware. And with the right software and the right incentives, it can become a grid asset, a virtual power plant that can help balance the system instead of breaking it. This idea is at the heart of the Electric Power Research Institute's DC Flex initiative. DC Flex is a 3-year effort to advance understanding of data center demand flexibility and test improvements under real-world conditions. It brings together more than 60 utilities, researchers, hyperscalers, and tech innovators, including Google, Meta, Oracle, NVIDIA, and Microsoft, along with grid operators and equipment suppliers. The goal is simple: to prove that data centers can actively support grid reliability by adjusting their load in response to grid signals. The core insight, and it is a beautiful one, is that data center workloads are not monolithic. They are a heterogeneous mix of interactive and batch processes. Some tasks, like serving a live web search or a real-time video call, are latency sensitive. They must run immediately. But other tasks, like training a new AI model, running a data backup, or performing a large file transfer, are not time-sensitive. Completing a training run a few hours later has minimal business impact. This is the flexibility that the industry has only recently begun to appreciate. Studies have shown that between 30% and 50% of current data center workloads are deferrable, a share expected to grow with the expansion of AI data centers. This is a staggering amount of flexible load, and the mechanisms for accessing it are already being developed. One is workload scheduling, the practice of delaying non-urgent computational tasks to periods of lower grid stress or lower electricity prices. This offers flexibility on a minute-to-hour timescale. Another is workload migration, which relocates computation to a different geographic region to exploit differences in electricity prices, policy incentives, or renewable energy availability. A third is clock rate modulation, or dynamic voltage and frequency scaling, which adjusts the power draw of individual processors in response to a grid signal. During an AI training run, underclocking a GPU can achieve about 50% power reduction with only 10% performance loss. This provides a fine-grained, second-scale response capability that is ideal for primary frequency regulation. The Phoenix demonstration, a DC Flex project involving Oracle, NVIDIA, and the local utility Salt River project, proved that this approach works. The demonstration showed that AI workloads contain inherent flexibility that traditional analysis had overlooked. Crucially, it proved that software-only orchestration can achieve meaningful flexibility without requiring expensive energy storage systems or hardware modifications. You don't need to build a new power plant or install a giant battery. You just need smarter software. The national impact of this approach could be staggering. EPRI studies estimate that the power-flexible reference design, if adopted nationwide, could unlock an estimated 100 gigawatts of capacity on the existing electricity system. That is equivalent to about 20% of total US electricity consumption. For context, data centers could consume 9% of US electricity generation by 2030, more than double current consumption. Unlocking 100 gigawatts of flexible capacity would meet projected AI growth for the next decade, without requiring extensive new generation or transmission infrastructure. The math is compelling. A steel mill or an AI data center that tolerates less than 100 hours of curtailment per year could allow utilities to provide many gigawatts of new capacity without proportionate transmission or generation expansion. A 2025 Duke University study reinforced this point, finding that controllable loads like Bitcoin mining could support up to 76 gigawatts of new US electricity demand with minimal curtailment of just 0.25% annually. Bitcoin miners can shut down operations within minutes to free up power for hospitals, homes, and AI data centers, which run at consistently high loads and cannot pause. In Texas, flexible loads, including Bitcoin mining, are expected to consume 54 billion kilowatt-hours in 2025, representing about 10% of the grid forecast, up roughly 60% year-over-year. The demand response role has historically accounted for 2 to 10% of miner revenues. This is a working model of load flexibility, already deployed and proving its value. But the shift to active flexibility is not without its tensions. A fierce debate is playing out in the PJM grid operator over whether this flexibility is real or merely a regulatory fiction. The Independent Market Monitor, the official watchdog of the PJM market, has sharply criticized the rapid addition of large data center loads that agreed to be flexible, arguing that the only way to ensure system reliability is for those loads to bring their own matching generation. The IMM argues that despite the hype, AI data centers cannot be relied on to turn off when the grid is stressed, and PJM doesn't have the ability or authority to force them to throttle. Allowing such massive loads to skip the line if they promise flexibility, as proposed by some stakeholders, would cost ratepayers billions of dollars. This is the central tension of the new paradigm. Flexibility is not a free lunch. It requires trust, verification, and enforceable agreements. The data center is not a charity. It will require incentives to maximize flexibility. The question is whether the grid can create the right market structures and operational frameworks to reward the flexibility that the data center can provide, while also protecting the system from the risk of that flexibility failing when it is most needed. It is a delicate, high-stakes balancing act. So, as you can see, the data center is evolving from a passive, chaotic load into an active, intelligent participant in grid stability. It is becoming a flexible, dispatchable resource that can help the grid manage its own stress. This is the most radical shift of all, and it could be the key to a sustainable, stable energy future. The grid of the AI age will not be a one-way street. It will be a two-way conversation, a complex, dynamic relationship between the machine and the system it depends on. In the final chapter, we will look at the future. We will bring all of these threads together: the containment of the grid-to-chip architecture, the sovereignty of the behind-the-meter microgrid, and the flexibility of the data center as a grid asset. We will see a vision of a new, smarter, more resilient power system, one that is designed from the ground up for the age of artificial intelligence. A system where the hammer blows are caught, the hum is dampened, and the heartbeat of the nation remains steady. A system where the AI data center is not a threat, but a partner. So, we have come to the end of this journey. We have traced the arc of a crisis that began with the insatiable hunger of artificial intelligence, and we have followed its path through the delicate physics of the electrical grid. We have felt the hammer blows of gigawatt load losses. We have watched the ghost of inertia haunt a system that is becoming faster and more fragile. We have seen the battery deployed as a shock absorber and the microgrid built as a fortress of sovereignty. We have listened to the hum that can shake the machine apart, and we have explored the architecture of containment designed to keep the beast within its cage. And finally, we have imagined a new role for the data center itself, not as a threat to the grid, but as a partner in its stability. Now it is time to bring all of these threads together, to see the shape of the new grid that is emerging from this collision of technologies. It is not a single solution. It is not a single technology. It is a new philosophy, a new architecture for the world's most complex machine. It is a system where the hammer blows are caught, the hum is dampened, and the heartbeat of the nation remains steady. A system where the AI data center is not a problem to be solved, but an integral part of the solution. The first layer of this new grid is the architecture of containment. This is the recognition that the AI data center is not just another customer, but a sovereign entity with its own unique demands. The grid-to-chip philosophy, championed by companies like Delta and Eaton, is the engineering response to this reality. By moving to higher DC voltages, integrating power and cooling, and using advanced power electronics, the data center can contain the immense density and volatility of its own load. It is the cage that holds the beast. The second layer is the architecture of sovereignty. This is the behind-the-meter microgrid, the private power plant that bypasses the public grid entirely. It is the ultimate expression of the need for speed and control. By building their own generation, data centers can avoid the multi-year interconnection queues and gain complete control over their energy supply. The battery energy storage system, acting as a buffer between the violent AI load and the slower responding turbines, is essential to this model. It smooths the load profile, protecting the expensive equipment and ensuring stable operation. The third layer is the architecture of flexibility. This is the recognition that the data center, with its mix of interactive and batch workloads, contains a vast reservoir of controllable load. By scheduling deferrable tasks, migrating workloads, and underclocking processors, the data center can actively support grid reliability. The DC Flex initiative is proving that this works in real-world demonstrations. The data center is no longer just a load. It is a virtual power plant, a flexible, dispatchable resource that can help balance the system. The fourth and final layer is the architecture of partnership. This is the most radical idea of all. It is the recognition that the relationship between the data center and the grid must be a two-way conversation. The grid cannot simply command the data center to reduce load. It must create the market structures and operational frameworks that reward flexibility. The data center, in turn, must commit to the transparency and reliability that the grid requires. It is a delicate, high-stakes balancing act. The political dimensions of this transition are beyond the scope of our story, but they are real. The conflict over who pays for grid upgrades, the push for federal land use for data centers, and the tension between innovation and regulation are all part of the larger narrative. But the engineering challenge is clear. The grid of the AI age must be smarter, more flexible, and more resilient than the grid of the 20th century. It must be able to handle the hammer blows of AI loads, the loss of inertia from renewable energy, and the emergence of a new class of dynamic, intelligent devices. The grid is no longer a one-way street. It is a complex, dynamic system, and the AI data center is both a challenge and an opportunity. We are already seeing the early signs of this new grid. In Texas, new regulations are allowing flexible loads to connect to the grid much faster than traditional loads. In PJM, the grid operator is developing new modeling requirements for computational loads. In Virginia, utilities are planning massive transmission upgrades to support the growing data center demand. And across the country, companies are deploying batteries, building microgrids, and developing software to manage the chaos. The future is not a single vision. It is a mosaic of solutions, each tailored to the specific challenges of a specific region. Some data centers will be connected to the grid, but with sophisticated controls that allow them to act as flexible assets. Others will be completely off-grid, powered by their own private microgrids. And others will be connected to new, dedicated transmission lines, built specifically to serve a cluster of facilities. The grid of the future will be more distributed, more resilient, and more intelligent than the grid of today. So, as you lie here tonight, consider this. The lights that illuminate your room, the phone that charges on your nightstand, the quiet hum of the refrigerator, all of them are connected to this vast, evolving machine. A machine that is being pushed to its limits by the very technologies that promise to reshape our world. The AI data center is not just a consumer of power. It is a force of nature. It is reshaping the grid, forcing a fundamental rethinking of how we generate, transmit, and consume electricity. The challenge is immense, but the solutions are emerging. The shock absorbers, the fortresses of sovereignty, the flexible loads, the partnerships, all of these are being built, piece by piece, by the engineers who are determined to keep the lights on. The grid of the future will not be the grid of the past. It will be smarter, it will be more resilient, and it will be powered, in part, by the same intelligence that is driving its transformation. The AI data center is not just a problem to be solved. It is a partner in building the new grid. The heartbeat of the nation will remain steady, but its rhythm will be different. It will be the rhythm of a new age, an age where the machine and the system work together. And that is a future worth building. Good night. So, we have traced the arc of this crisis through the physics of the grid, the architecture of the data center, and the engineering of the solutions. But there is one more element to this story, one that is perhaps the most unpredictable and the most human of all. It is the people in the control rooms, the grid operators, the men and women who sit in front of banks of screens, watching the pulse of the nation and making split-second decisions that can keep the lights on or plunge millions into darkness. Their job has always been difficult, but the AI data center has made it almost impossibly complex. Let's step into that control room. It is a room that looks like something out of a science fiction film. Walls covered in massive video displays showing the status of thousands of miles of transmission lines, hundreds of power plants, and millions of customers. The operators sit in tiered rows, like air traffic controllers, each responsible for a specific region of the grid. Their job is to maintain the balance, to keep generation and demand perfectly matched, second by second, minute by minute, hour by hour. They are the guardians of the 60 Hz heartbeat. For decades, this job was predictable. The load followed patterns. Morning, when people wake up, there is a surge in demand. Evening, when people come home, another surge. Weekends are different from weekdays. Summers are different from winters. The operators had models, decades of historical data, and a deep intuition for how the grid would behave. They could anticipate problems before they happened. They could watch the load curves and see the shape of the day unfolding. It was a steady, if sometimes stressful, rhythm. Then the AI data centers arrived, and the rhythm broke. The load curves that the operators had relied on for decades are no longer smooth. They are jagged. They are violent. A single training run can cause a spike of hundreds of megawatts in milliseconds, and then, just as suddenly, it can vanish. The operators can no longer anticipate what the load will do. They can't see the shape of the day. They are flying blind. The tools they have been trained on, the models they have used for years, are suddenly inadequate. The AI data center is a black box to them, a source of chaotic, unpredictable behavior that they cannot control. This is the human dimension of the crisis. The operators are not technophobes. They are highly trained engineers and technicians. but they are being asked to manage a system that is fundamentally different from the one they were trained for. The grid is no longer a predictable machine. It is a dynamic, unstable system, and the operators are struggling to keep up. The stress is immense. A single mistake can have catastrophic consequences. In 2003, a single operator working in a control room in Ohio misread a set of alarms and failed to take corrective action. Within hours, 50 million people were without power. The blackout cascaded across 8 states and into Canada. That was caused by a tree branch and a human error. Now imagine the same situation, but with hundreds of AI data centers, all pulsing and surging unpredictably. The margin for error is gone. The operators are also dealing with a new kind of threat. In the past, a disturbance was usually caused by something physical, a storm, a lightning strike, a piece of equipment failing. These events were visible. They could be seen on the screens. Now the disturbances are invisible. They are the result of algorithms running in data centers hundreds of miles away. The operators can see the frequency dip, but they don't always know why. They don't know if it's a data center disconnecting, or a generator tripping, or something else entirely. They are operating in a fog of uncertainty. This is where the human factor becomes critical. The best control systems in the world are only as good as the people who operate them. And those people are being pushed to their limits. The training programs that have been in place for decades are no longer sufficient. Operators need to understand the behavior of AI loads, the characteristics of inverter-based resources, and the complexities of a low-inertia grid. They need new tools, new models, and new ways of thinking. Some companies are starting to address this. They are incorporating AI itself into the training process. Using machine learning to simulate grid events, giving operators the chance to practice responding to scenarios that they might never see in the real world. They are building more sophisticated alarm systems that can filter out the noise and highlight the critical information. They are designing control rooms that are more intuitive, reducing the cognitive load on the operators. But there is a deeper challenge. It is the challenge of trust. The operators need to trust the tools that are being given to them. They need to trust the models that are predicting grid behavior. They need to trust the automation that is making decisions. And they need to trust each other. The control room is a team environment, and the team needs to function seamlessly under extreme stress. This is not just about technology, it is about culture. The culture of the control room has to change. Operators need to be encouraged to speak up, to challenge assumptions, to question the data. They need to be empowered to make decisions, even under uncertainty. The old command and control model, where the senior operator makes all the decisions, is no longer adequate. The team needs to function as a distributed intelligence, where every member contributes. The AI data center is not just a technical problem, it is a human problem. It is a problem of training, of culture, of trust, and of decision-making under uncertainty. The engineers are building new systems, new batteries, new controls, and new architectures. But those systems will only work if the people operating them are prepared. The human element is the final frontier of this crisis, and it is the one that is most often overlooked. The industry is waking up to this reality. The North American Electric Reliability Corporation, or NERC, has issued new guidelines for operator training. The Federal Energy Regulatory Commission, or FERC, is requiring grid operators to develop new tools for managing the integration of AI loads. The Electric Power Research Institute, or EPRI, is studying the human factors of grid operation in the age of AI. The issue is being taken seriously, but the challenge is immense. The operators are being asked to manage a system that is changing faster than they can adapt. The AI data center is not waiting for them. It is expanding, demanding more power, creating more disturbances, and increasing the stress on the grid. The operators are on the front line of this battle, and they need all the support they can get. So, as you lie here tonight, Think about the people in those control rooms. They are the unseen guardians of the grid. They are the ones who keep the lights on, who prevent the blackouts, who manage the chaos. They are the human element in a system that is becoming increasingly automated. And they are the ones who will ultimately determine whether the AI age is a story of progress or a story of collapse. The technology is important, but it is the people who matter most. In the next chapter, we will look at the economics of this crisis. We will see who pays for the upgrades, who profits from the growth, and who is left holding the bill. Because the AI revolution is not just an engineering challenge, it is an economic one. And the costs are already showing up on your utility bill. So we have walked through the physics of the grid, the architecture of the data centers, the engineering of the solutions, and the human element of the operators in the control rooms. But there is one more layer to this story, one that touches every single person who pays an electricity bill. It is the economics of the crisis. The question of who pays for the upgrades, who profits from the growth, and who is left holding the bill. Because the AI revolution is not just an engineering challenge, it is an economic one, and the costs are already showing up on your utility bill. Let's start with the scale of the problem. The electrical grid was built over the course of a century. It was designed for a world of slow, predictable growth. Now the AI industry is demanding a massive, rapid expansion of that infrastructure. New transmission lines, new substations, new transformers, new power plants. All of this costs money, a lot of money. The estimates are staggering. The total cost of upgrading the grid to meet AI demand is projected to be in the trillions of dollars. And the question is, who pays? In the traditional model, the cost of grid upgrades is spread across all ratepayers. When a utility needs to build a new transmission line, it goes to the State Public Utility Commission and asks for permission to recover the cost through higher rates. The Commission approves it, and the cost is spread across all customers. This is how the grid has been funded for over a century. It is a system of socialized costs. Everyone pays a little bit, and everyone benefits from a more reliable grid. But the AI data center is not everyone. It is a specific customer with a specific demand and a specific impact on the grid. And the question is whether it is fair for all ratepayers to subsidize the expansion of the grid for the benefit of a few massive corporations. This is the central tension of the economics of the AI grid. The data centers are profitable. They are generating enormous revenues for companies like Google, Microsoft, Amazon, and Meta. They are creating immense value for their shareholders, but the costs of their grid integration are being spread across all ratepayers, including those who cannot afford it, the elderly couple on a fixed income, the single parent working 2 jobs, the small business owner trying to keep the lights on. They are all paying for the AI revolution, whether they use it or not. The numbers are revealing. A recent analysis by the Union of Concerned Scientists, a non-profit research organization, found that data centers are already increasing electricity bills in 7 states. The report, titled "Data Centers Are Already Increasing Your Energy Bills, We Have the Receipts," documented over $4 billion in connection costs being passed to consumers. In some areas, residential electricity bills are projected to rise by as much as $70 per month. That is a significant burden for many families, and this is just the beginning. The grid upgrades needed to support the next wave of AI growth will be far more expensive. The transmission infrastructure alone, the high-voltage lines and substations, is projected to cost over $100 billion in the next decade, and that does not include the cost of new generation, the natural gas plants, the nuclear reactors, and the massive battery storage systems. The total bill could be in the trillions. The data center companies are not paying their fair share. In many cases, they are receiving massive tax breaks and subsidies from state and local governments. In Virginia, the state with the largest concentration of data centers, the industry has received over $1 billion in tax breaks. In Ohio, Meta received a 100% property tax abatement for 15 years on its data center campus. In Texas, the industry benefits from a deregulated energy market that allows them to bypass many of the costs that other customers must bear. This is a classic case of privatization of profits and socialization of costs. The data center companies reap the benefits of the AI boom, while the costs of the infrastructure they depend on are spread across all ratepayers. It is a system that is fundamentally unfair, and it is generating growing resentment among consumers and policymakers alike. The debate is playing out in public utility commissions across the country. Consumer advocates are challenging the cost recovery mechanisms that utilities are using to fund grid upgrades. They are arguing that the costs should be borne by the data centers themselves, through higher connection fees, dedicated rates, or direct investments in infrastructure. The industry is pushing back, arguing that the grid upgrades benefit everyone, not just data centers, and that spreading the costs is the most efficient way to fund the expansion. The independent market monitor for the PJM grid operator, the organization that oversees the grid across 13 Mid-Atlantic and Midwest states, has been particularly vocal on this issue. The monitor has argued that data centers are using the grid in ways that were never anticipated, and that they are not paying their fair share. The monitor has called for new rules that would require data centers to pay for the full cost of their grid integration, including the cost of new transmission lines and substations. The economics of the AI grid are also affecting the reliability of the system. The rapid growth of data center demand is straining the grid in ways that are causing reliability concerns. The North American Electric Reliability Corporation, or NERC, has warned that the grid is becoming less stable and that the risk of blackouts is increasing. The cost of that risk is being borne by all consumers. When the grid fails, everyone suffers, regardless of whether they use AI. The economic challenge is not just about who pays, it is also about who profits. The companies that are building the AI infrastructure are generating enormous profits. NVIDIA, the leading supplier of AI chips, is now one of the most valuable companies in the world. Its market capitalization exceeds $5 trillion. The cloud providers, Amazon, Microsoft, and Google, are generating billions of dollars in revenue from AI services. The data center developers, companies like Equinix and Digital Realty, are seeing their stocks soar. But the economic benefits are not flowing to the communities that are hosting the data centers. The jobs created by data centers are minimal. A large facility might employ a few dozen people. The tax revenues are often offset by the tax breaks that the industry receives. The economic benefits are going to shareholders and executives, not to the local communities. This is creating a growing sense of resentment among residents who feel that they are bearing the costs of the AI revolution without seeing any of the benefits. The economic challenge is also affecting the pace of the build-out. The data center companies are demanding power faster than the grid can deliver it. They are building their own power plants, bypassing the grid, and creating a fragmented, inefficient system. This is driving up costs for everyone, and it is creating a race to the bottom among states competing for data center investment. The states that offer the most generous tax breaks and the most lenient regulations are winning the competition, while the states that are trying to protect their ratepayers are losing out. This is a race to the bottom that is not sustainable. The costs of the AI grid are going to be borne by someone, and if it is not the data center companies, it will be the ratepayers. The system needs to change. There are proposals for reform. Some advocates are calling for a federal tax on data center electricity consumption, with the revenue used to fund grid upgrades and offset ratepayer costs. Others are calling for a requirement that data centers pay for the full cost of their grid integration, including the cost of new transmission lines and substations. Still others are calling for a pause on new data center construction until the economic and environmental impacts can be fully assessed. The economics of the AI grid are a complex and contentious issue. There are no easy answers. But one thing is clear: the current system is not sustainable. The costs are being shifted to the most vulnerable ratepayers, while the profits are being captured by the wealthiest corporations. This is a recipe for social unrest and political backlash. The AI revolution will only be sustainable if it is fair, and that means that the companies that are profiting from it must pay their fair share. So, as you lie here tonight, consider this: the lights in your home, the charge on your phone, the power keeping your refrigerator cold. All of it is connected to this vast economic machine, a machine that is being pushed to its limits by the very technologies that promise to reshape our world. The AI data center is not just a consumer of power, it is a driver of economic inequality. The costs are being shifted to you, while the profits are being captured by others. This is not just an engineering challenge, it is a challenge of fairness, of justice, and of the social contract. And it is a challenge that we must all confront. In the next chapter, we will look at the global picture. We will see how other countries are grappling with the same challenges and what we can learn from their approaches. Because the AI revolution is not just an American story, it is a global story, and the solutions will need to be global as well. So, we have traced the arc of this crisis through the physics of the grid, the architecture of the data centers, the engineering of the solutions, the human element of the operators, and the economics of who pays. But the AI revolution is not just an American story, it is a global story. Data centers are being built all over the world, from the green hills of Ireland to the deserts of the Middle East, from the cold fjords of Scandinavia to the dense cities of Southeast Asia. And each region is grappling with the same challenges: the hammer blows of AI load, the loss of inertia, the need for new infrastructure, and the question of who pays. Let's start with Europe. The European grid is different from the American grid in several important ways. It is more interconnected, with high-voltage direct current links between countries that allow power to flow across borders. It is also more heavily reliant on renewable energy, with a significant share of wind and solar power on the system. This makes the European grid even more sensitive to the loss of inertia than the American grid. The European grid operators are already dealing with the challenges of integrating renewables, and the AI data center is adding a new layer of complexity. The response in Europe has been proactive. The European Network of Transmission System Operators, or ENTSO-E, has issued guidelines for the integration of large loads, including data centers. The guidelines require data centers to provide detailed information about their load characteristics, including their power draw, ramp rates, and protection settings. They also require data centers to participate in frequency response services, helping to stabilize the grid when disturbances occur. This is a recognition that the data center is not just a load, but a participant in the grid. Several European countries are also exploring innovative solutions. In Ireland, where data centers are projected to consume over 30% of the country's electricity by 2030, the grid operator has imposed a moratorium on new data center connections in the Dublin area. The moratorium is designed to give the grid time to catch up and to ensure that new data centers are located in areas with adequate transmission capacity. This is a blunt but effective approach to managing the growth of AI load. In the Nordic countries, where renewable energy is abundant, data centers are being built to take advantage of the cheap, clean power. But there is also a recognition that the grid must be strengthened to handle the new load. In Sweden, the grid operator has announced a major investment in transmission infrastructure, including new high-voltage lines and substations to support the growing data center industry. The investment is being funded through a combination of utility rates and direct contributions from data center developers. The European approach is more regulatory and coordinated than the American approach. There is a recognition that the grid is a shared resource and that all users must contribute to its maintenance and expansion. This is reflected in the policies of the European Union, which has issued directives on the integration of large loads and the development of smart grids. The EU is also funding research into new technologies, including grid-forming inverters, battery storage, and demand response. Now let's look at Asia, where the picture is very different. China is the world's largest builder of data centers, and the country is aggressively expanding its grid to support the AI industry. The Chinese approach is top-down and state-directed. The government is building massive new transmission lines, nuclear reactors, and renewable energy projects to meet the growing demand for electricity. The scale of the investment is staggering. China is expected to invest over $1 trillion in grid infrastructure over the next decade, far more than any other country. The Chinese grid is also more centralized and more controlled than the American grid. The government has the authority to direct investment, to set prices, and to manage demand. This allows the Chinese to move faster and more decisively than the Americans. The Chinese are also investing heavily in new technologies, including grid-forming inverters, battery storage, and advanced transmission systems. The goal is to create a smart grid that can handle the demands of the AI age. But China also faces challenges. The country is heavily reliant on coal, which creates serious environmental problems. The transition to renewable energy is happening, but it is slow and fraught with difficulties. The AI industry is growing faster than the grid can keep up, creating strain on the system. The Chinese are also dealing with the same issues of inertia and stability that are plaguing the Americans. The solutions are similar: batteries, grid-forming inverters, and demand response. Japan is another important player in the Asian AI scene. The country has a highly developed grid, but it is also vulnerable to natural disasters, including earthquakes and tsunamis. The Japanese approach to grid management is cautious and methodical. The government has issued guidelines for the integration of data centers, and grid operators are working with data center developers to ensure that new facilities are connected in a way that maintains system stability. The Japanese are also investing in battery storage and grid-forming inverters, recognizing that the loss of inertia is a growing concern. Now let's look at the Middle East. Countries like the United Arab Emirates and Saudi Arabia are investing heavily in AI and data centers. The motivation is diversification. These countries are trying to move away from their dependence on oil and build a future based on technology and services. The grid in the Middle East is relatively new and robust, with ample capacity for growth. But there are also challenges. The extreme heat creates demands for cooling that are far greater than in other regions. The data centers in the Middle East are among the most power-hungry in the world. The solution in the Middle East is solar power. The region has abundant sunshine, and solar energy is becoming increasingly cost-competitive. Data centers in the Middle East are often paired with large solar farms, creating a self-contained energy system. The batteries store excess energy during the day, and the data center runs on that stored energy at night. This is a model of sustainability that is being watched closely by other regions. Now let's look at the developing world. Countries like India, Brazil, and South Africa are also building data centers, but their grids are often less robust than those in the developed world. The challenges are greater. The grids are older, more fragile, and less capable of handling the demands of AI. The governments in these countries are facing a choice: invest in grid upgrades or fall behind in the AI race. The choice is difficult because the investment is enormous and the benefits are uncertain. The developing world is also dealing with issues of access and equity. The AI revolution is creating a digital divide, where the wealthy countries benefit from the technology while the poorer countries are left behind. The data centers are being built in the wealthy countries, where the power is reliable and the infrastructure is strong. The developing world is being left out, and there is a growing concern that the benefits of AI will not be shared equally. The global picture is one of divergence. The wealthy countries are investing in grid upgrades and building the infrastructure for the AI age. The developing countries are struggling to keep up. The result is a two-speed world, where the AI revolution is happening in some places and not in others. This is a source of tension and inequality, and it is likely to be a major issue in the coming decades. So, as you lie here tonight, consider this. The AI revolution is a global phenomenon, but its impacts are not evenly distributed. The wealthy countries are building the grids that will power the future, while the developing countries are being left behind. The costs of the transition are being borne by ratepayers everywhere, but the benefits are flowing to a small group of wealthy corporations and nations. The challenge of the AI grid is not just a challenge of engineering and economics. It is a challenge of global equity. And it is a challenge that we must all confront. In the next chapter, we will look at the future of the chips themselves. We will see how the next generation of GPUs will push the limits of power density even further, and what that means for the grid and the data center. Because the AI revolution is accelerating, and the next leap in computing power will require an even more dramatic leap in energy infrastructure. So, we have journeyed across the globe, examining how different regions are grappling with the challenge of powering the AI revolution. But the story does not end with the grid of today. The AI industry is evolving at a breathtaking pace, and the next generation of chips will push the limits of power density even further. The GPUs of the future will be even more powerful, and they will demand even more energy. This will create new challenges for the grid and new opportunities for innovation. Let's start with the trajectory of the chips themselves. The current generation of AI chips, like NVIDIA's H100 and B200, are already consuming remarkable amounts of power. The B200, for example, draws roughly 1,000 watts per chip. A full rack, like the NVL72, can exceed 120 kilowatts. But this is just the beginning. The next generation of chips, already being designed, will push these numbers much higher. The future lies in extreme-scale chips. These are chips that are not just faster, but much larger and much more power-hungry. Companies are already talking about chips that consume 2,000 watts per processor and racks that consume over 600 kilowatts. Some industry leaders are projecting that the 1 megawatt rack will be a reality within the next few years. To put that number in perspective, 1 megawatt is enough to power roughly 800 average American homes. And an AI data center will have hundreds of these racks. This is not just a linear increase in power, it is an exponential one. The power density of AI chips is growing faster than the ability of the grid to keep up. The grid is already straining under the current load, and the next generation of chips will make the problem far worse. The hammer blows will be more violent, the hums will be more intense, the need for solutions will be more urgent. The engineers are not standing still. They are developing new technologies to address the challenge of power density. One of the most promising is the shift to three-dimensional chip design. Instead of laying the transistors flat on a silicon wafer, the engineers are stacking them vertically, like a skyscraper. This creates a much denser chip with more computing power in a smaller space. But it also creates a much more concentrated heat source. The cooling challenge becomes even more extreme. Another promising technology is the use of new materials. Silicon has been the foundation of the semiconductor industry for decades, but it is reaching its limits. The engineers are exploring new materials like gallium nitride and silicon carbide that can handle higher temperatures and higher power densities. These materials are already being used in power electronics, and they are making their way into the chips themselves. The architecture of the chips is also evolving. Instead of having separate chips for computation and memory, the engineers are integrating them on the same piece of silicon. This reduces the distance that data has to travel, improving speed and reducing power consumption. But it also creates new challenges for cooling and power delivery. The cooling challenge is perhaps the most daunting. As the power density increases, the amount of heat that must be removed also increases. Air cooling, which has been the standard for decades, is no longer sufficient. The industry is shifting to liquid cooling, and some of the most advanced data centers are exploring immersion cooling, where the chips are submerged in a non-conductive fluid. This allows for much higher power densities, but it also requires new infrastructure and new maintenance procedures. The power delivery challenge is equally daunting. The copper cables that deliver power to the chips are reaching their limits. At high currents, the copper wires generate heat and create voltage drops. The industry is exploring new materials, like aluminum and carbon nanotubes, that can conduct electricity with less resistance. They are also exploring higher voltages, like the 800-volt DC systems that we discussed in earlier chapters. The future of the data center will be a world of extreme density. The chips will be packed tightly together, drawing immense power and generating immense heat. The cooling systems will be more sophisticated, and the power delivery systems will be more complex. The data center will be less like a building and more like a machine, a seamless integration of compute, power, and cooling. But the data center does not exist in isolation. It is connected to the grid, and the grid is also evolving. The new transmission lines, substations, and transformers are being designed to handle the immense power demands of the AI age. The battery storage systems are being scaled up to provide the fast frequency response that the grid needs. The grid-forming inverters are being deployed to provide the virtual inertia that the grid is losing. The smart controls are being developed to manage the dynamic load. The challenge is to synchronize the evolution of the chips and the evolution of the grid. The chips are evolving at a rapid pace, driven by Moore's law and the demands of the AI industry. The grid is evolving more slowly, constrained by physics, economics, and regulation. The gap between the two is growing, and this is the source of the crisis. The solution is innovation. New technologies, new materials, and new architectures are needed to bridge the gap. The engineers are working on all of these fronts. They are developing more efficient chips, more advanced cooling, and more intelligent controls. They are designing new grid infrastructure, new battery systems, and new market structures. The pace of innovation is accelerating, and the solutions are emerging. But there is a limit to what technology can do. The laws of physics are immutable. At some point, the chips will reach a fundamental limit. The transistors cannot get much smaller. The heat cannot be removed any faster. The power cannot be delivered more efficiently. The AI industry will need to find new ways to compute, new architectures that are less power-hungry, and new algorithms that are more efficient. This is the frontier of the future. The AI age is not just about scaling up, it is also about scaling down. The engineers are exploring new computing paradigms like neuromorphic computing, quantum computing, and optical computing. These approaches promise to be far more power efficient than the current digital computing, but they are in their early stages, and it will be many years before they are ready for prime time. So, as you lie here tonight, consider this. The next generation of chips will be even more powerful and even more power-hungry than the current generation. The demands on the grid will be even greater, and the challenges will be even more intense. The engineers are racing to develop new solutions, but the clock is ticking. The AI revolution is accelerating, and the grid must keep up. The future of the grid will be a world of extreme density, extreme power, and extreme challenges. But it will also be a world of innovation, of creativity, and of progress. And that is a future worth building. In the final chapter, we will bring all of these threads together. We will look at the vision of the grid in 2050. We will see a world where AI and the grid are fully integrated, where the hammer blows are caught, the hums are dampened, and the heartbeat of the nation remains steady. We will see a world where the AI data center is not a problem to be solved, but a partner in building the future. So, we have come to the final chapter of this journey. We have traced the arc of a crisis that began with the insatiable hunger of artificial intelligence and we have followed its path through the delicate physics of the electrical grid. We have felt the hammer blows of gigawatt load losses. We have watched the ghost of inertia haunt a system that is becoming faster and more fragile. We have seen the battery deployed as a shock absorber and the microgrid built as a fortress of sovereignty. We have listened to the hum that can shake the machine apart, and we have explored the architecture of containment designed to keep the beast within its cage. We have examined the human element of the operators, the economics of who pays, the global picture of how different regions are coping, and the future of the chips that will push power density even further. Now it is time to look forward, to see the vision of the grid in the year 2050. Not as a prediction, but as a possibility, a vision of what could be if we make the right choices, invest in the right technologies, and build the right institutions. A vision of a world where the AI data center is not a threat to the grid, but a partner in its stability. A world where the hammer blows are caught, the hums are dampened, and the heartbeat of the nation remains steady. A world where the grid of the AI age is smarter, more resilient, and more equitable than the grid of the 20th century. Let's start with the physical infrastructure. By 2050, the grid will have undergone a massive transformation. The transmission system will be expanded and upgraded, with new high-voltage lines and substations connecting the data centers to the sources of power. The distribution system will be smarter, with sensors and controls that allow the grid to monitor and manage the flow of electricity in real time. The transformers will be more efficient, and the cables will be made of new materials that can carry more power with less loss. The generation mix will be radically different. By 2050, renewable energy will be the dominant source of electricity. Solar and wind power will be abundant and cheap, and they will be complemented by battery storage and other forms of energy storage. The grid will be flexible and resilient, able to handle the variability of renewable energy and the dynamic demands of AI data centers. Nuclear power will also play a role. The new generation of small modular reactors, or SMRs, will be deployed at scale. These reactors will be factory-built, modular, and safe. They will provide a steady, reliable source of carbon-free power for data centers and other large loads. The fusion reactors, which are currently in development, will also begin to come online. Fusion promises to provide virtually unlimited, clean, and safe power. It is the holy grail of energy, and by 2050, it could be a reality. The data centers themselves will be transformed. The grid-to-chip philosophy will be fully implemented, with high-voltage DC power delivery, advanced cooling, and integrated energy storage. The data center will be a seamless integration of compute, power, and cooling. The chips will be densely packed, drawing immense power and generating immense heat, but the cooling systems will be up to the task. The data center will be less like a building and more like a machine, a finely tuned instrument of the digital age. The battery energy storage systems will be ubiquitous. Every data center will have its own battery bank, providing fast frequency response and backup power. The batteries will be large, efficient, and long-lasting. They will be charged during periods of low demand and discharged during periods of high demand, smoothing the load on the grid. They will also provide virtual inertia, compensating for the loss of physical inertia from the retirement of traditional power plants. The controls will be intelligent. The grid will be managed by advanced software, using artificial intelligence to predict demand, manage supply, and respond to disturbances. The AI that is causing the crisis will also be part of the solution. It will optimize the operation of the grid, reducing waste and improving efficiency. It will coordinate the charging and discharging of batteries, the ramping of power plants, and the response to disturbances. The grid will be self-healing, able to isolate faults and restore service quickly. The microgrids will be integrated into the larger system. Some data centers will be completely off-grid, powered by their own generation and storage. Others will be connected to the grid, but with sophisticated controls that allow them to act as flexible assets. The microgrids will be interconnected, creating a distributed, resilient system that can withstand disturbances and recover quickly. The economics will be fairer. The data center companies will pay their fair share for grid upgrades. The costs will be allocated based on the principle that the cost causer is the cost payer. The ratepayers will not be burdened with the costs of the AI revolution. The profits of the AI industry will be shared more broadly, benefiting the communities that host the data centers and the workers who build and operate them. The human element will be better supported. The operators will be better trained and better equipped. The control rooms will be more intuitive and the tools will be more sophisticated. The operators will have real-time information about the behavior of AI loads, and they will be able to anticipate disturbances before they occur. The team culture will be collaborative and supportive, with every member empowered to make decisions and contribute to the mission. The global picture will be more equitable. The developing countries will not be left behind. They will invest in their grids, build data centers, and participate in the AI revolution. The technology will be shared, and the benefits will be distributed more evenly. The digital divide will narrow, and the AI revolution will be a force for global progress. This is the vision. A world where the grid of the AI age is smarter, more resilient, and more equitable than the grid of the 20th century. A world where the hammer blows are caught, the hums are dampened, and the heartbeat of the nation remains steady. A world where the AI data center is not a problem to be solved, but a partner in building the future. But this vision is not guaranteed. It requires investment, innovation, and political will. It requires that we make the right choices, now, today. It requires that we recognize the challenge and confront it with courage and determination. The AI revolution is not going away. It is accelerating, and it will reshape our world in ways that we cannot fully imagine. The question is whether we will shape it, or whether it will shape us. So, as you lie here tonight, consider this. The lights in your room, the phone on your nightstand, the quiet hum of the refrigerator, all of them are connected to this vast, evolving machine. A machine that is being pushed to its limits by the very technologies that promise to reshape our world. The AI data center is not just a consumer of power. It is a force of nature. It is reshaping the grid, forcing a fundamental rethinking of how we generate, transmit, and consume electricity. The challenge is immense, but the solutions are emerging. The shock absorbers, the fortresses of sovereignty, the flexible loads, the partnerships, all of these are being built, piece by piece, by the engineers who are determined to keep the lights on. The grid of the future will not be the grid of the past. It will be smarter, it will be more resilient, and it will be powered in part by the same intelligence that is driving its transformation. The AI data center is not just a problem to be solved, it is a partner in building the new grid. The heartbeat of the nation will remain steady, but its rhythm will be different. It will be the rhythm of a new age, an age where the machine and the system work together. And that is a future worth building. So, rest easy tonight. The engineers are working on it. The operators are watching over it. The grid is evolving. The future is uncertain, but it is full of possibility. And that is enough to carry with you into sleep. Good night.